Our next panel discussion is on quantum accelerated supercomputing, pioneering the convergence of QPUs and GPUs. Moderating this panel is Dr. Celia Merzbacher, who is the Executive Director of the Quantum Economic Development Consortium, QED-C, a consortium that aims to enable and grow the U.S. quantum industry. QED is supported by the National Institute of Standards and Technology, NIST, and nearly 250 industry, academic, and other members. Please welcome Dr. Celia Merzbacher and her panelists.
We're going to go ahead and use the... Thank you, Carl. Yeah, it's great to be here, and thanks to Connected DMV for organizing this event, bringing together such a broad community. I'm Celia Merzbacher, Executive Director of QED-C, and I'm delighted to have with me two thought leaders from the community. The session title, as you heard, is Quantum Accelerated Supercomputing, Pioneering the Convergence of QPUs and GPUs, and we might as well add CPUs to that list as well. So what we're really going to be covering is some of the sort of bleeding edge technology developments in terms of providing the ultimate sort of performance. The panelists that I have with me today are John Levy. John's worked at the intersection of technology and finance for more than 35 years. He's CEO, chair, and co-founder of SEEQ. And prior to co-founding SEEQ in 2018, he served as the chair of Hypris. With him also here on the stage is Sam Stanwyck. He leads the product team for quantum computing at NVIDIA. Prior to joining NVIDIA, he worked at Rigetti Computing and Keysight Technologies. So really deep expertise. And I will just briefly say, we don't have a lot of time. I don't know, we have a clock here somewhere, but that Sam has his PhD from Stanford and John has an MBA from Harvard, so I think we've got a lot of credibility in our panel today. So I'll jump right into it, and John, why don't you tell us a little bit about SEEQ?
Yeah, thank you.
Not everybody may know it.
Yeah, thank you, and thank you for having me here today. It's great to be here with Sam as well. And what we're building at SEEQ is we're building essentially a quantum computer on a chip. And when we think about quantum computers and QPUs, so-called, we often think just about the qubits themselves, but we have to think about them systematically: readout, control, error correction, multiplexing, reset, et cetera. And what we've done is we've taken all of that functionality and put it on a chip so that essentially, you know, we're used to seeing a quantum computer with racks of equipment and connectivity and everything, and you know, you can't see it very well from where you are, but maybe that's the point. That for us is a quantum computer. And that's really where we're starting. And then the last thing is that we're building this with entirely digital stack. So this is a digital chip. So we can think of it almost as being a hybrid in that way, where the qubits are quantum and all the functionality is digital.
Fantastic. That's really exciting, especially for folks who are used to having the whole sort of behind the curtain, all that equipment, right, and other necessary technologies today. So I think everybody has heard of NVIDIA, but we'd like to hear from you, Sam. What's NVIDIA doing in the quantum space?
Sure, and yeah, first, thank you for having me here. It's an honor to be here today. So NVIDIA is not building a quantum computer, but what we've done for a long time is build, you know, leading edge accelerated computing technology and the platforms to make that accessible to everyone. And so this has been first in gaming, then HPC and AI and many other disciplines, and now it's quantum computing. And so what that means is, you know, a platform for quantum research and development, all the way from simulating quantum computers so that researchers can get a head start on algorithm and application development, to, you know, mostly what we're going to talk about today, which is what does useful quantum computing look like in the future, and how is quantum computing going to fit in with the rest of accelerated computing technology. And that's where we partner with companies like SEEQ, and in general, we seek to partner with and enable the entire quantum ecosystem.
Great. Maybe it would be worth just defining some terms. So what do you mean, John, when you talk about quantum HPC or quantum supercomputing?
Right, so I think there are two parts to it. So one of them has to do with the idea of scaling quantum computers to the enterprise level. And when we say scaling, and by the way, SEEQ means Scalable Energy Efficient Quantum Computing. It's an acronym. And so it's really core to what we think about. And we're thinking about trying to build, fault-tolerant, error-corrected systems operating in real time at the data center level. And so that's one part. The other part of that is the integration of other kinds of compute, so CPUs and GPUs, so that we have an integrated system. It feels like that it's a single node, and so that you're actually thinking about that. We think almost that computing becomes the combination of all of these things, and we don't really have to think about them as QPU, CPU, GPU. They're just available to us in an integrated fashion.
Great. I mean, maybe it's a little like the early hybrid electric gas, it's like you step on the gas, you go, whatever's powering it in a way.
That's right.
So Sam, what are QHPCs going to enable? What does NVIDIA think that is going to be made possible by this technology?
Yeah, big question. I'd say there's a long-term perspective and a more kind of immediate midterm perspective. I think the long-term perspective, we know about the promising applications of quantum computers in many different verticals. We also know that quantum computers are not going to stand alone, especially as they scale up. The classical compute needed to do everything else and run the classical side of the application is going to scale up as well and become more and more important. And so thinking long-term, we really see it as quantum accelerated supercomputers, where just like GPUs became an essential part of today's supercomputers, quantum computers are going to increasingly fit in. But importantly, in the near term and midterm, I think it's also about what can the integration of quantum and classical do for quantum computers. Right. So a lot of the things needed to get the most out of quantum computers are going to take high-performance classical compute, are going to take AI. And so if that's pre-processing and compilation, if that's optimal control or calibration using reinforcement learning, or error correction decoding, we expect that there's quite a lot of value to be given to quantum computers with the integration of classical computers, GPUs, AI, and so on.
Yeah, I mean, if you think about error correction as an example of that, there's a certain amount that we can do on chip right next to, in close proximity to qubits, right on top of qubits. And we'll do that, but we also know that there's a certain amount that needs to be done on kind of a global basis. And that's where we need to be able to have the resources of, say, a GPU, but we need to do it in order to make it real time. We have to make sure that we reduce the latencies, that we have very fast chips, and that we have sufficient bandwidth to be able to do that. And it's that kind of connectivity that I think is really critical to making that work.
Yeah, absolutely. So I think there are a whole host of engineering challenges and scientific challenges to improving the quantum computers themselves. But then for this integration and thinking about how to build a quantum accelerated supercomputer, there are those challenges like maximizing latency, getting the right bandwidth. And so working on that now and investing in that now is also really important.
Yeah, and one other example I would say is looking at it from the application side. So we do work with BASF and Merck, et cetera. And the requirement for all the work that we do is error correction. But if we go beyond that and think about using a quantum computer to develop novel candidates, and then using the classical resources to be able to validate those candidates, come back and say, now let's learn about what we, why that candidate was better than maybe the previous version. And we do that, and we use AI resources to be able to do that, to help us generate a new candidate, and then have this iterative cycle going back and forth, I think is exactly the kind of process that we can imagine with the kind of customers that we already have.
So it sounds like there's a lot of sort of parts of that effort that need to be addressed.
Yeah.
What are some of the technology or real bottlenecks in terms of realizing this capability, and especially maybe outside of your organizations, what can the community focus on to help make progress faster?
Yeah, so I think as quantum, well, first of all, I think fidelity of the quantum computers is limiting now, but there are, in terms of tackling the scaling and integration challenges, there's kind of a low-level system side, like how do we bring enough compute close enough to the quantum computer with low enough latency to do error correction on the timescales of a quantum computer, which are very, very fast. So that's a tough engineering challenge. I think going to the complete opposite end, there's how do you program such a system, and how can we make it so that domain scientists who work on supercomputers now can start to develop on quantum accelerated supercomputers.
How far up the stack do you go, actually?
Yeah, so for NVIDIA, we have a programming model called CUDA-Quantum, which is analogous to an open source quantum version of CUDA. And so that's quantum programs expressed in Python and C++, which are compiled down to an IR where they can be executed on either quantum processors or simulators. So ideally all the way to the developer and researcher.
And how do researchers use that? Is it available? Do they work with NVIDIA in a partnership?
Yeah, so it's available today, free, open source, and so we have many partnerships, including with SEEQ, including with many end users, but people also kind of take it and develop on their own.
Great. So sort of from where you're sitting, John, what are some of the technical areas that you're really focusing on these days?
Right, I mentioned that our chips are digital, and one of the advantages of being digital is that we can overcome a lot of the latencies that are inherent in a lot of more analog-oriented systems. We don't have to have the number of amplifiers and attenuators and filters, et cetera. And so it enables us to be able to make direct connections to CPUs and GPUs, and that's kind of the collaboration that we're building is all around that. And Sam, you were mentioning before this issue around being able to operate in the timescale of a quantum computer, doing everything we can to reduce latencies, increase speed, have sufficient bandwidth. This is the core requirement for us to really get to a point where we can build fault-tolerant quantum computers. And that, I think, goes to the core of what we're working on and exploring together.
Excellent. I want to just take the last couple of minutes to kind of open the aperture and ask for your thoughts. Here we are in Washington. A lot of different stakeholders are in the audience. In terms of sort of externalities, what can government do? What can others do? What are the sort of non-technical policies and pain points that you're dealing with or thinking about? Maybe we'll start with Sam.
Yeah, so I guess first of all, in the biggest aperture, I think quantum is exactly the kind of thing that's perfect for government investment because it's something that kind of takes long-term vision. It's something that there won't be tons and tons of value near-term in the private sector compared to the value long-term. In terms of the things government should be investing in, maybe I'll leave it to John for more specifics. But I'd say kind of good to have the end goal in mind of what does quantum computing that delivers a lot of value look like, and invest in that, even if it takes a long time.
Patient capital.
Yeah, I think that the idea of thinking about quantum computers as quantum data centers, number one, I think is really, really important. Number two is this idea of having quantum computers that operate in a kind of heterogeneous fashion with QPUs, CPUs, and GPUs, and being able to demonstrate that. I mean, this sort of chip-to-chip direct connectivity is really novel. And it needs the kind of support, I think, of governments, both in terms of the development and then ultimately as a buyer and user of this technology, to both shape it and support it. That's one big area. The second area, I think, and we look at the world from a chip-centric perspective. I think you do too, even though we both have software that supports our chips. And making sure that we have things like the CHIPS Act that would be, and I know there are efforts in Europe to do the same thing, to be able to support the needs of chips that go in quantum computers. They're very different than chips that go in classical computers. And so we really need to think broadly about supporting superconductors and related technologies. From sort of an investment and support perspective.
Great. Well, that's a fantastic, I think, endpoint. I'm just going to ask you, I'm going to ask, I think, a rhetorical question. So are NVIDIA and SEEQ looking for qualified talent these days? The workforce an issue for us?
Yeah, we are. Plenty of job postings available. I think, we're looking for people, not just with quantum engineering backgrounds or quantum physics backgrounds, but software engineering who can bring that to the table. And I think that's sort of generally a trend, kind of experts with bringing other expertise, maybe from classical supercomputing into quantum computing, which kind of relates to what we were talking about how the technologies need to integrate.
Yeah, and for us, it's hard, as I think everybody knows, to recruit people into the quantum space. Incorporating that into the chip space and then doing what we do with single flux quantum, which is its own special area, creates an enormous challenge for us and identifying talent.
Well, I encourage folks who maybe know young people or are interested in knowing more to catch John and Sam during the conference today. So I want to thank you both. It's been fantastic. We ran out of time before we kind of covered everything we wanted to, but I really appreciate your time, and thank you again.
Thanks.
Thank you.
Thanks.